Hey all, welcome back. It's time to look at the 2018 E&M exam and figure out what the heck's going on. So I bid you to have your exams either online or once you wrote your notebook out, because here we go. We're going to do some of the questions, not all, because some of them are magnetic. So first question deals with a metal plate. Now here's what I want you to think. Even though these are two distances away, they tell you that the distance that it goes is much less than A, the size of the plate. What this is secretly saying is that it's a uniform field. Like a capacitor. These plates are super wide and tall compared to this distance in here. So if you're trying to use this equation, that's for a point charge. It doesn't apply here because it's such a wide plate that it's pretty much uniform. And in a uniform field, it's the same field whether it's close or far, which is why I have answer C for number 1. Question 2 says, what is the kinetic energy to go from X to Y if the electric field is E and it's a positive charge released from rest? So the answer is A, and you got that because kinetic energy secretly means work. Work is the change in kinetic energy, which is a negative change in potential. From your formula sheet, change in potential energy for a charge is Q delta V, where delta V is the voltage. Let's see voltage here. Looking at your formula sheet again, voltage, or change in voltage is a negative integral of EdR. Since electric field is constant in this case, it's just ER. So I put everything together. I put voltage as ER, where R is D, and it's negative, and a negative, the negatives cancel out the positive. Positive QED, and there we are. But then, we're now going to look at a bunch of capacitors. So this is kind of a cool little question here. You have C1 and C2. They tell you that C1 has a value of C, and C2 is 1/3 of that. And that together, they are CEQ. So here's how I kind of approach this. C1 is C, C2 is C over 3. When you put them together, you get 2 CEQ, right? I'm sorry, you get CEQ. So here's my equation. C1 and C2 is CEQ because they're in parallel. And then they tell you when you insert a dielectric, it's now 2 CEQ. So what I did is I said, okay, there should be a kappa here. The capacitance of the first one, which hasn't changed, plus the new capacitance, which is kappa C over 3, is now going to be twice as much as it was before. Okay. So putting all that in there, I actually solved this for kappa, and I got 5. So again, I just set what it was before versus what it was after. Now, question number 4 is kind of a beginnings of flux. This is kind of a flux-heavy and magnetic-heavy exam, which surprises me. There are a bunch of questions on flux, which I didn't really expect. Maybe 2, but like 5? Ugh. So let's kind of review it a little bit. True for a Gaussian surface. This is the surface you make. The net flux is 0. So if you can't remember, net flux is this symbol, and it's really either side of the equation. It's the EdA integral or the Q enclosed over epsilon naught. Both of those are flux. So obviously, if you have no flux, you can't have any Q enclosed. And if you have no flux with an area, you must have no electric field. So there's no charge inside. There's the net charge is 0 otherwise. And the electric field is 0. These are things that could be true, so all 3 have to be true. And we are still going on, my friends, because on this exam, we have a bunch of magnetic stuff falling in until we get to question number 8. A parallel plate capacitor, okay, there we are, has air between them. This air has a kappa of 1. It is charged up and disconnected. If something's disconnected, that means Q is now fixed and the voltage can change. So what we're going to do is we're going to stick something between there. Stick it in between there means that the capacitance must go up. And since Q is fixed, the voltage goes down. But I'm looking at capacitance and electric field. And from the earlier equation, voltage is integral of ED. And again, for a capacitor, the distance here is so small compared to the plates that it's pretty much a uniform field because it is a uniform field, which means that it's just ED. If voltage goes down, electric field must go down. And that's why it's got to be C. And then there's more flux stuff. Again, this is what threw me for a loop. Here we have 2 charges, X and Y, and they're enclosed in this Gaussian surface. They tell you the flux is positive flux for X and negative 4 flux for Y. So that could be either one of these two. So now, number 9, you put them both together. What's now the total electric flux of the surface? Well, it's kind of like everything enclosed. you had positive flux and negative 4 flux. So if you add them up, you get negative 3 flux, and that's what's enclosed. Yay, that's kind of easy. Number 10, they touch, and now you surround X. Well, X is going to change now. Since this is equivalent to flux and epsilon is a constant, you can think of the system as having like positive flux and negative 4 flux, total of negative 3 flux for the system, as we found earlier. And if they touch, you're each going to get half of that. It's kind of like charges. If 2 charges touch, you each get half of the total charge. So that means they're going to get this much flux afterwards, which is B. And finally, number 11, you bring Y nearby. Well, bringing Y closer does not change Q enclosed of X. So that means the net flux does not change. That's also saying net flux is constant, but I can't write because I'm illiterate. So we know bringing Y closer, the net flux will remain constant. But what's going to happen, however, is you're going to get more field lines because it's closer. But since more lines go in and more lines come out, the net still remains the same. And that's why it's answer E. And then we got a bunch of magnet stuff. We're going to page 3 right now because screw that. Magnet. And then we get to questions 17 and 18. Here's my cute little triangle. Positive Q, negative Q, positive Q. It asks you which one has the highest potential. Potential means voltage, and highest means most positive. As a reminder, a positive charge makes a positive voltage, which you think of as like peaks of a valley. A negative charge makes a negative voltage, which is like a valley. You might remember the voltage is only 0 when it's between a positive and a negative. So if I want to have the highest one, I want to be either at one of these points, which is not happening, or I want to be to the closest to the positives and furthest to the negatives. The only one that does that is this point right down here, which is answer D. Then for number 18, which one has the electric field to the left and top? Well, I kind of did them here. You might remember that positive charges have an outward field, negative charges have an inward field. So I kind of just drew arrows. Like for example here, you'd have a positive, this would be from this Q, the other one would be from the other Q, and there's a negative inward one. Add them all up, you get a big downward one. The only one that has it is this point right here, because it has an up from this one, a kind of away from the other one, and an inward one. These combined equal that. And we're strumming along. Number 24 is next. We have 2 stationary charges with an electric field of 0 between them. So you can see here, Q1 and Q2, right here, in the middle point, R and R, the electric field has to be 0. The first thing you have to know is that they must be the same sign, because you want both of these to cancel out. If one was positive, one was negative, for example, fields go out of positive and inward negative, there's no way they can cancel out, they're both going right. And mathematically, you know electrical field for a point charge is Q over 4 pi epsilon naught R squared. They both have the same R, so therefore the only thing that happens is that Q1 has to equal Q2 in magnitude. They must be the same sign, and they must have the same amount. That's what B says. And then look at 25, the best number ever. We have an RC circuit. What happens here is the capacitor starts off fully charged, and then we're figuring out what happens to the resistor's voltage. You can probably imagine, after a long time, this thing empties, which means there's no more voltage here. So the voltage is at 0. And the first moment you have the max voltage, because the biggest difference here, as time goes on, these two plates are going to equalize, meaning the voltage goes down. So this is going to start off with lots of voltage, ends with 0. That has to be B. The reason why it's a curve, again, because it have that e to the minus t over tau relationship you might remember from before, where tau is the RC. And now we're looking at question 28. We have 3 capacitors trying to find the CEQ here. Well, these two are in series. Series, you know, is the whole 1 over thing when it comes to capacitors. So C and C gives you C over 2. That's in parallel with this C. And when they're in parallel, you add them up, and you get 3C over 2, or 1.5C, which is pretty easy. Then we have this one. I kind of did this differently than they suggested, but I don't care. We have 2 circuits. When you put a resistance R here, you get a current I. When you triple the resistance, you only get half the current. We got to find what little r is. So what I said here is that I said in the first circuit, you have V equals IR. Those two things are in series, you add them up. In the second circuit, you get V equals IR, but new R and nu I. And since these both have the same voltage, I just set them equal to each other and solve for little r. And what I got was the weird relationship that little r equals big R, which is true, which makes sense. If these two are the same, this is 2R, and here you get 4R, twice the resistance, half the current. And now to question number 30. Hey, what's the energy in dielectric? Well, the capacitance goes up, by definition. Give me point, yay. And now we're at question 31. We see this dang triangle again. Come on now, peeps. Positive Q, negative Q, and point P. We're trying to find the potential energy stored in this configuration. Now, what that means is you're trying to find the potential energy due to these two things. Because nothing else matters. So what we're going to do is we're going to say on the formula sheet, potential energy is Q change in voltage. Well, you're like, which Q we have here? Well, it's easy. You pick one Q and the other one's the one making a voltage. So I'm going to say, I'm going to choose the positive Q and the voltage at the positive Q due to the negative Q. Okay? Voltage due to a charge is just 4 pi epsilon naught distance over the charge. Putting this all together, you get negative Q squared over 4 pi epsilon naught A. And that happens to be answer E. So that's awesome. Once again, voltage equals ED, again, for this kind of this weird thing. And solving for, solving for voltage, you get 4 pi epsilon naught d squared q times d when the d's cancel out. That's how I understood what this was. Now, question number 32. The potential at point B due to two spheres. Okay, voltage. Well, we're at equal distances with equal charges. I'm guessing that's going to be 0. This is a peak, this is a valley. They're going to be the same distance away, same charge, are going to cancel out. Try to remind you of this, right? The middle of positive Q and negative Q, it's got to be 0. Or you can simply say the voltage here is the sum of the two voltages. This voltage is positive Q over 4 pi epsilon naught A. The other one is negative Q over 4 pi epsilon naught A. They have to equal 0. Life is great. And then finally, number 33, the direction of the electric field at point P. Well, lines go out from positive into negative. That equals right. And that's to the right, to the right, to the right, which is 33. And my friends, the last two questions, again, deal with magnets. So now it's time to go to our wonderful friend, the FRQ. And FRQs this year, again, they have one from each of the 3 topics, which means we're only going to do 2 of these. And so here's the first one. This circuit here. Voltage, resistance, 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 switch. Okay. Question number 1A. Calculate the current measured at A1 when it's open. Well, this kind of reduces down to the following circuit. These 2 branches are just straight up parallel. 6 and 12, 12 and 6. So what we're going to do is V equals IR using the entire thing. So because this is open, these 2 are in series, and it's like just 2 parallel circuits. So we have 18 and 18. 2 things in parallel, they're equal, they split in half. So the total resistance is going to equal 11 here. V equals IR, 20 equals I times 11. And I get that annoying 1.82 amps. That's the current through A1 because A1 gets all of it. Now to calculate the voltage that shows here, this is the voltage up to 12. Well, I know that it gets half that current, which is 0.909. Because it's 18 and 18, they're going to split up equally. And so I'm going to do V equals IR. The current's 0.909, and the resistance of that is 12, and I get a beautiful number of 10.9 volts. Claro. Then you close the switch. Oh, geez. Calculate the current. Okay. I'm going to redraw this. Actually, you know what? I'm going to do it up here because I'm a boss like that. When this is closed, these 2 things are in parallel and these 2 in parallel. So it looks like this. This is a little easier way of making you think about it. This is kind of a switch right here, whatever. So we have a 6 and 12, and we have a 12 and 6. So let's find the resistance of this. So 6 and 12, when you do that, you get 4, and you get 4 here. So I have 4, 8, 10. I got a resistance of 10. And the voltage is 20, so it means the current's going to be 2 amps. Life is good. And then it says calculate the potential difference now of voltmeter V. Okay. So my trick here is I said, oh, I know that the 6 and 12, which is a parallel branch, is equal to 4 ohms. I know the current through the total branch is going to be 2 amps because, again, this reduces down, all the current goes through the entire thing. V equals IR. I get 8 volts for this parallel branch. And in parallel, for resistors, they have the same voltage. So it's just 8 volts for each branch. Then a student, those dang students, want to determine if there's a current in the closed switch. Yeah, there is. How do I know? Here's your current. At this point, it splits up. Black and green. Hey guys, which one's going to have more current, the black or the green one? Yep, the black one, because it has less resistance. But then, it's going to switch. This is black, and this is green now. Which means that some current's got to go this way. Because we have low and high flows, high and low flow. So current's going that way. So now we're going to figure out the current measured by the ammeter in this situation, letter C. Which what I did here is I said, okay, let's find the current between these two. So looking up here, I know both of these are 8 volts. And by the same logic, these are also 8 volts down here, but I don't have to worry about that. I found the current for each branch. This was 1.33. This was 0.66. And here I get 1.33 and 0.66. Which means there better be 0.666 going this way. Because here you have 1.33 and you only have 0.66. Wait, I switch these up because I'm a dumbass. I'm so sorry. This goes from 1.33 down to the smaller 0.666. So it lost half its current. So that's the current going through there. And which way is it going? Obviously, it's going from X to Y, which would be right. Explanation, because this, you could even say the junction rule, because at this point you got 0.666 going out, 1.33 going in, so you have to have 0.66 going out. But we're still not done, because that dang student replaced the switch with the capacitor. What are they thinking? That would be just attention city for me. So at this point, we have a capacitor in there, it's 12 microfarads. And after a long time, calculate the charge stored. So here's what you're thinking. Long time means this is full, meaning that there's no flow through it. We're back in situation 1. So in situation, the first situation, answer A. So we know in answer A that the beginning part, the current is 1.82. And now I'm going to do some voltage stuff. 1.82 coming out here. At this point, I'm going to use V equals IR. Here's 20 volts. I calculated the voltage loss here to be 3.64, which means the voltage at these points is 16.36. Then, knowing the currents I found before, the next thing it is I found the voltage drop here. This dropped by, I think, around 6 or so, and I got this point to be 10.91. This dropped by double that. I ended up with 5.43 or so. I want to find Q? Easy. Q equals CV. I know the capacitance is 12 microfarads. The voltage is the difference between these two, which happens to be 5.432 or 5.43, whatever it is. And then with a charge of around 6.55 times 10 to the minus 6, they said it was 65 microcoulombs. Oh wait, 6.55 times 10 to the minus 5, I'm so sorry, which is 65 microcoulombs. And that makes the next one super easy. Which point X or Y is higher? Well, it's going to be X. Why? Because I found it to be 10.91. Also, electricity flows this way, obviously, and electricity flows from high to low voltage. So that was not a bad FRQ. And then look at this thing. Yeah, we don't have to do it because you guys are missing out on stupid magnet stuff, which is not bad because this is actually a cool Ampere's Law question, which makes me sad. So I'm going to secretly pour some tea out tonight and cry myself while my cats cry to me as well, looking for tuna, which I haven't got them in a while. But then we have this thing. Last and certainly least, this third question with charge densities. Ugh. Charge density for a plate is charge over area. So we have D and we have positive and negative charge densities. Let's find the energy for inside a capacitor. Looking at my formula sheet, I see energy 1/2 Q delta V or 1/2 C delta V squared. Both of these are not actually as helpful as you think. I want to have Q in there, so I'm going to use this one. However, the voltage is kind of ugly, so I'm going to use Q equals CV. So voltage is Q over C, so I get 1/2 Q squared over C, which is the actual equation. Okay. I want this to be in terms of these things. Well, I don't see C there. I don't see Q there, but I do have this. So I'm going to expand out. Capacitance is epsilon naught A over D. With cap in there, we don't care about cap because it's there. So then C on the bottom gives you epsilon naught A over D. So that's, I don't know why I scratch it out, but we're good. But now I need I don't want Q in there. Well, I know that sigma is Q over A. I have a Q squared, I need an A squared. So what I'm going to do right now is I'm going to multiply both sides by A over A, which is 1. And this is epsilon squared. I'm sorry, it's sigma squared. It's the charge density squared. And so this is what I get. Sigma squared dA, that's actually like a distance in A, it's not like dA. So it's not calculus, so I'll just do this. Over 2 epsilon naught. Kind of a weird, tough question because of the fact that it involves some algebraic juggling and thinking. Then, for the next ones, we put a metal slab inside of it, and we're trying to figure out the electric field. So I'm going to draw it in. Electric field goes from positive to negative. But because it's metal, inside the metal, the electric field is 0, because it's a conductor. In the figure below, draw an arrow. Oh, it just did that. Okay, yep. It's 0 inside, it's down at first and down at second. You can think of it as like, this is a negative region, this is a positive region. Same idea. C, on the lines below, rank the regions. Well, if it's a uniform field, because again, this distance is nowhere near as big as this distance, then it's uniform, which means that the top and the bottom have the same, and the other one has 0. And so this is your ranking. Is the capacitance greater, less, or equal to? Oh, come on, greater. Justify it. Kappa. Or capacitance is kappa epsilon naught A over D. Kappa equals 1 for air, everything else is greater than 1. Rokishi should be proud of me, that's my computer logic right there, else. Finally, letter E. When charged, the original charge density is energy stored more or less of the same. Okay. It's less. First region, logic. I told you before, capacitors store energy through the electric field, but now we have a region where the electric field is 0. So the electric field is not everywhere, so it's got to be less. And you have a mathematical reason. Mathematical reason? This is on your formula sheet. This stays fixed when you put the dielectric inside, but this goes up. And if that goes up, the energy's got to go down. And now we're on this. We have a graph of voltage versus slab thickness. So think of it this way. Here's your thickness. As it gets thicker and thicker and thicker, that means that the voltage goes less and less and less, obviously. Hey, when will the voltage be 0? Duh, when this entire thing is filled. So this right here is to be the distance between the plates, because the voltage goes to 0. Hey, we just answered this. Again, the reason why is because as this gets thicker, as more of the metal takes up the capacitor, you're going to have a less and less electric field, which means you have less and less voltage. Now we can figure out the charge density. To do this, charge density again is Q over A. And since Q equals CV, Q is going to be epsilon naught A over D times V. And so solving for V over D, because that's what I have here, and oh, look at this, Q over epsilon naught A. I know what that is. Sorry, Q over A. I get the original function. So if I want to find the charge density, I'm going to take the slope of this line and divide it by epsilon naught once I've done centimeters. And you should get around 2 times 10 to the minus 9th coulombs per meter squared. Hey guys, that was E&M kind of done. I appreciate your time and concern. Love you all.